Today I typed up my notes because I think you'll probably be able to read the typed up version rather than me just writing out with my own handwriting, which isn't too good. Just as a reminder, in class today, which is Friday, I'm creating this on Friday, I wanted you to do page 121, numbers 5 through 19, and some other problems too. We didn't quite get through number 19 in my classes, so as part of your homework this weekend, I would like you to go all the way up in your new calculus textbook to question number 19. I think we might have stopped at like 16 or 17, so just if you can finish those up all the way to 19, that would be great. But today I'm going to talk to you about rates of change and the difference between an average rate of change versus an instantaneous rate of change. Remember, the slope is just a visual depiction of the rate. The slope is rise over run, and rise over run tells you the rate at which y changes compared to x. For example, one of the most common rates that we talk about is the number of miles driven versus the amount of time it takes us to drive. So let's say if y is the number of miles driven and x is the number of hours we have driven, then what you get is the familiar rate of change of miles per hour, because it would be the change in miles divided by the change in hours. So miles per hour is just a rate of change of your position, actually. And that's just a familiar rate, an average rate versus, we'll talk about average versus instantaneous. If you take any 2 points on a graph, whether it's a straight line graph or a curved graph, you can find an average rate of change by finding the slope of a straight line in between them, or you can just actually calculate y2 minus y1 over x2 minus x1. So I'll show you an average rate of change with this graph. This graph has an equation. You should write this down. This equation is y is equal to negative 3x cubed plus 18x squared minus 36x plus 26. If you wanted to put that into your graphing calculator, you would see that this graph is going to be coming up. So here's your original function. F of x is equal to that cubic function, reflected cubic function. If I wanted to find the average rate of change, let's say the average rate of change between this point on the graph and this point on the graph, I just connect a line between them, and the average rate of change between 1, 5 and 3, negative 1 is, the slope is negative, and negative rise over run would be a negative 3. So the average rate of change between the 2 points 1, 5 and 2, 2 is change in y over change in x. Excuse me. So 2 minus 5 is negative 3, and 2 minus 1 is 1. So the slope, or the average rate of change, would be negative 3, just between those 2 points. But what we're doing is we're finding derivatives of functions, and if you find the derivative of a function, we could find the derivative of this function, and we will, and we plug in some particular x value, what we get is not an average rate of change between 2 points, but we get something called an instantaneous rate of change at a particular value. And an example that I like to give is, let's say I drive to Albany, and it is a 50-mile trip, and it takes me 1 hour. So my average speed, or my average rate of driving, is 50 miles per 1 hour, or 50 mph. That is the average speed of my whole trip to Albany. But along the way, I've driven on the thruway, and I've probably gone 65 miles per hour at some point. I've driven through the city of Kingston with all of its stoplights and stop signs, so my speed will be 0 miles per hour. Those are instantaneous rates of change, or instantaneous rates. When I'm at a stop sign, my speed is 0. When I'm going on the thruway, at any particular moment of time, I might be driving 65 miles per hour. So those are instantaneous rates of change at any particular moment, your speed. But if you take an average time or miles per hour, then that's your average speed, and that's the difference between the average rate of change and an instantaneous rate. So right now we've got an average rate of change between these 2 points. Let's try to figure out an instantaneous rate of change, maybe at this particular point, 2. So to get an instantaneous rate, what we're going to do is take the derivative of this function. So y prime, this is just a simple product or power rule. So the y prime would be equal to negative 9x squared plus 36x minus 36. And so we can plug in any x values that we want. We can get a rate of change, an instantaneous rate of change when x equals 1. If we plug in x equals 1, it would be negative 9 plus 36 minus 36. So this instantaneous rate of change would be negative 9 right here at this point. If I plugged in x equals 2, I would get an instantaneous rate of change right here at this point. So we could do y prime when x is equal to 2. So that would be negative 9 times 2 squared, which is 4, plus 36 times 2 minus 36. And this is negative 36 plus negative 36 is negative 72. Plus 72 is equal to 0. So this instantaneous rate of change right here would be 0. And that's actually the slope of the tangent line here. The slope of the tangent line here would be negative 9. And I'm sure that if we plugged in x equals 3, because of the symmetry of this graph, this rate of change would also be negative 9. So that's just a difference between average rate of change, which you just calculate the slope between 2 points, and an instantaneous rate of change when you're finding a derivative of a function and then plugging that x value in to that derivative. The last thing I want to talk to you about today is that there are 3 cases where derivatives actually do not exist. Those 3 cases, if you can't draw a tangent line at a particular point on a graph, then there is no derivative. So keep that in mind when we talk about these 3 cases. First of all, there is no derivative at any type of discontinuity. There is no derivative at any hole, gap, or jump in a graph. And for example, I'll just draw some examples for you. If you remember back in chapter 1, I think it was, when we were drawing some functions, sometimes we would get a straight line graph and it would have a hole in it at one particular spot. So if we come to a graph like this, and maybe x is equal to 4 in this particular graph, there is no derivative, or the derivative does not exist at this point. Maybe this is a 1 over here. There is no derivative, or the derivative does not exist at the point 4, 1, because there's a hole in this graph. There's a derivative every other place on this graph, but not at that particular point 4, 1. If you have the step function, or the greatest integer function, if you remember that, it was just a series of steps. And there's a derivative of this function in between each one of these circles, but there's no derivative. Here's x equals 1, here's x equals 2, here's x equals 3. The derivative does not exist at all of these x values, 1, 2, 3, or any integers. So no derivative at x equals 0, 1, 2, 3. This says y is equal to the greatest integer of x, if you remember that function, the step function. Or if you have a piecewise function that's got a big jump in it also, there's no derivative where there's a jump in the graph. So that's the first case. Second case, there's no derivative if you have a sharp turn, or sometimes sharp turns are called cusps. And the most familiar example of this is the absolute value function. If you remember, y is equal to the absolute value of x. There's a derivative of the absolute value function at all places on this graph except at x equals 0. Because there's a sharp turn right here, you can't really figure out where the tangent line would be. If, would it be that way or that way? So there's no derivative at x is equal to 0. Or in other words, at the point 0, 0, there's no derivative. And there's some other graphs that have sharp turns in them. There's a graph that looks like this that we'll be looking at some of those other types of graphs. But anytime you have a sharp turn, you have no derivative at that particular point. In other words, the graph has got to be smooth and continuous. If a function has a vertical inflection point, what that means is if you have a graph that comes up and then all of a sudden starts becoming vertical for just one point right here, this is called a vertical inflection point. If we were to draw a tangent line to this graph at this particular point, this tangent is vertical. And what's the slope of a vertical line? Well, the slope of a vertical line is there's no slope or it's undefined. So whenever the slope is undefined, there is no derivative at that particular point. And we'll be looking at some graphs that actually have a vertical tangent. So those are the three cases, and we're going to be doing some worksheets on Monday that have to do with the average rate of change versus the instantaneous rate, and we'll look at some cases, or we'll look at some other particular functions where the derivatives do not exist at certain points along those graphs. So congratulations, another nice short video, and have a great weekend. I'll see you Monday.